Hello, everyone, and welcome to episode 3. In episode 3, we're going to learn how to make graphs, but using to show the relationship between two variables. In the last episode, you guys learned how to identify the independent variable, dependent variable, and constant. So we're going to practice that skill again, and then we're going to learn how to graph an independent variable and a dependent variable in a line graph. So if we take a look at the experiment here, it says in an experiment, a company is testing if the weight of a bat, and again, obviously I make typos, so this should not be there, determines how far the ball can be hit. So to perform this experiment, a company has a person hit a baseball off a tee 10 times with different bats and measure the average distance the ball travels. So just in case you don't know what this looks like, so this is a video of someone hitting a baseball off a bat. So here we have the ball, here we have the bat, and in this experiment, we're going to be using, if we were actually doing this experiment, we would be using bats of different weights, and a person would hit the ball off the tee, and we would measure how far the ball will travel. And again, that's a pretty far distance. A tape measure would be difficult. In actual MLB baseball, they use Google satellite or Google data to map how far baseballs are hit by actual players during a Major League Baseball game. So that's sort of what we're investigating. Again, does the weight of the bat affect how far a ball can be hit? So here we want to identify our independent variable. So our independent variable, if you remember, is something that the person doing the experiment is changing. So in this experiment, if you're thinking about it in your head, what the person is changing is the weight of the baseball bat. And then, so what are we trying to see? Well, the dependent variable is what the person is measuring to see the effect that the independent variable has. So if we look into the data, we'll often see the word measure or record. So here, the person is recording the average distance that the ball travels after being hit. Now, just to note, the word average means that they're doing it multiple times. So let's say they hit the ball 10 times. They would measure the distance 10 times and divide by 10 to get the average distance. So now constants are things that we want to remain the same. So that the only thing that is affecting how far the ball travels is the weight of the ball. So that we could name these forever. But one thing you would want to change is the size. Wouldn't want to change is the size of the ball, the type of ball. Bats can be made of different things. So the material of the bat. Also, a Major League Baseball player is going to hit the ball further than I can. So the person hitting the ball. I mean, you could name these things forever. So there's not really one right answer. But again, that's one of the problems when you're designing the experiments, is that you want to design an experiment that keeps almost everything constant, and the only thing that is changing is the independent variable, and that is difficult in experiments. So if we actually had data, this is a X and Y axis, and if you take a look, if you know in math, you usually have 4 quadrants. A lot of times in science, not all the time, but we only use the positive values. That's not going to be true all the time, but a lot of times that is true, that you're only using quadrant 1 of a graph because you're only taking positive X values and positive Y values. If you take physics, you're going to learn that that's not true all the time. So when you're making a graph, okay, and you're labeling your axes, your independent variable, which in this case is the distance that this time is the weight of the bat, goes on the x-axis, which is the bottom axis, and you want to label it with the units. And again, we're going to practice this graphing, this actual data, on a graph on the next page. And then your independent variable, so your dependent variable, goes on the y-axis, and you also want to put the units that it's measured in. Again, we talked about possible units that can be used to measure in episode 1. So if you want to go back to episode 1, you can check that out. All right, so we're actually going to graph this data, and I'm going to graph it on Kami, but it is difficult to graph on Kami. So if you can print this out, you feel free to print it out. But again, I'm going to struggle with the graph on Kami, so you can too. So here we look at the data. We have our independent variable, which when you get a chart is usually first. And then we have our dependent variable. And just take a look. We're measuring the weight of the bat in pounds. And if this was truly science, we would measure probably the weight of the bat in kilograms. But in the United States, when we play baseball, they measure the weight of the bat in either pounds or even sometimes ounces. So we're going to be measuring the weight of the bat in pounds and the average distance the ball travels in meters. In Major League Baseball, they do actually measure the distance the ball travels on home runs in feet. Again, because we do not use the metric system, and meters is a metric unit. But I figured we would do one non-metric system unit and one metric system unit. So the first thing you need to do when you're making a graph is give it a title. So you want your title to be pretty specific about what it's measuring. So here we're measuring the weight of the bat versus how far the ball travels. And again, this title could be a little bit more descriptive, but if you're ever stuck on making a title, you can put the independent variable, which is the weight of the bat, and then the dependent variable, which is how far the ball travels. So the next thing we want to do is put a label. So remember, our independent variable goes on the x-axis, and I'm actually going to write it below the line because I got to number my axis here. So my independent variable, remember, is the weight of the bat. And we need to put the units we're measuring in pounds. And just so you know, the abbreviation for pounds is LBS. Or you could just put pounds if you want to. And then for the label on the y-axis, we're measuring how far the ball travels. I don't want to run into the graph. And we're measuring that in meters. All right. So now we need to determine how much each line is going up by. And I'm going to zoom into this graph so that we can see it a little bit better in a second, because you're going to have to put numbers, and this is going to be difficult on Kami again, if you can print it out. So sometimes you can just play it by ear. So like, for example, I'm going to explain more on the y-axis. If you look at the x-axis, every single time the value of the weight is going up by a half. It's like going up in equal amounts. So we can just go up by a half. So I'm going to zoom in, but you're going to see that the y-axis is a little bit more difficult. So I'm going to zoom in a little bit to the y-axis line so that we can label them and look at them better. All right. So when you're making your graph, and we'll talk about ways to not, I'm going to lower my font so I can fit more numbers. You can sometimes not start at 0. You would have to do a broken line, but we're going to start at 0. And then I'm going up by 0.5. So this line is 0.5. Again, I'm just using the text tool. If you want to try to write it, you can. It's hard. This is 1. This is 1.5. This is 2. 2.5. 3. 3.5. 4. And we want to make sure we got to the top point, and I forget what that was. So it was 4. We can stop. Or you can go up the rest of the way if you want. I'll go to 5. You don't really have to, but sometimes it's good to go a little bit past in case you get extra data if you do the experiment with a heavier bat. All right, so now that I've labeled and with my x-axis and with the 3 things, so the what is being measured, the units that it's measured in, and I numbered it so it's going up in equal lengths. We now need to do the same thing for our y-axis. So our y-axis is a little bit more difficult because the numbers are not going up in equal intervals. And so students struggle often, knowing what number is good to go up by. So I have sort of made a formula that I suggest you write down. That kind of works. So to figure out what you want to go up by, you can take the biggest number in the data set and divide it by the number of boxes on the axes. So the biggest number in our data set, if we're looking here, is 125. And I'm going to go down to my graph and I'm going to count the number of boxes. I got to zoom out a little bit. So if I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So there's 20 boxes. So I'm going to divide this 125 number by 20, And I'm going to do that in the calculator. So in my calculator, I'm pressing 125, the division sign, which is the one with the dots, the two dots in the line in the middle. Sorry, 125. So 125 divided by the number of, and then I'm getting the 125 because this is the biggest number in the data set. All right, I'm going to divide that by 20. It's not going to be a nice number as my computer decides to show things about the data. All right, so, and I'm going to divide that by 20 and I get 6.25. All right, so what that means is that you can go up by any number that's bigger than 6.25, and it will make it. Now, generally, we want to go up by a number that's easy to count by. So you could go up by 7, but that's not easier to count by. 8 is a little bit easier to count by. I'm just going to go up by 10s because 10s seem like an easy number to count by, and it's not much, it's not double 6.25. So I'm going to go up by 10s. So again, I'm going to zoom in again so that I can, I zoomed out. I'm going to zoom in again so that I can label my axes, and I need my text box. So we have 0 already, so we don't have to re-put that. This is 10, and this is going to be a little bit harder to do because each number is not vertical. I'm going to have to type it. This is 20. This is 30, and I have to get all the way to 120. Now, if you're good at this, you can skip numbers. I'm going to label all of them, but you could go up by only label every even. You could go. This could be. You could put 10, 30. You could skip some writing some numbers. But for the purposes of just you don't have to do that. And some people have trouble counting. I'll do every number, although it's going to take some time. 80. Excuse me. 90. 100. And again, obviously, if we had paper, this would be a lot easier. We would be done already. And now my text box is going away. There we go. 100. Almost there. 110. And then 120. And again, if you're done before me, feel free to fast forward. All right, so we've labeled our axes, and our last job is to label the points. So I'm going to do this in red. And so our first point is 165. That one is easy to find. So 1, and then 65 is in the middle, so somewhere around there. And again, this is not going to be perfect because we're doing it on Kami. And then we have our next number is 1.587. So here, 1.5, here's 1.5, and then here's 80, so closer to 90, but not so around there. And then 102. So here's our 2, and 102 is going to be around there. Again, we're just estimating if it's not on the line. 25, 2.5, 125. Oh, I missed. I need to go up one more. So 125. Hold on, I lost my spot. So 2.5, 125 would be here. We need to add 130 in that spot. I'll do it in a second. I didn't go up to the top number. So then 110, we're at 3, 110, which would be here. All right, and that one's nice on the number. All right, and then we have 3.595, which is right here. And then we have 4 and 72. Now, would I say that this is a perfect graph? I mean, I don't use the whole axis, so it's not, I could have gone up by a smaller number here, but it basically shows what happens. And technically, you should not connect a line between the points because that means you're assuming you know what happens between these 2 points. And again, let me make sure that my axis goes up to the right number of numbers, which is 130 up here. All right, and then once I add 130, our graph is done. Let's just go over the important things that need to be included in the graph. So we have our title, which has to mention both the independent and the dependent variable. We have our x-axis, which has the independent variable and the units, and it goes up by even amount each line. To do that, we have this formula, which is the biggest number in the data set divided by 20. And that helps us so that we make sure that we make it. We don't waste time not making it to the end of the graph. And then we have our y-axis, which once again has the units. So now I'm going to zoom out again so that we can look at all the questions on this lovely data set. And I just want to make sure that we are recording. We are. All right. So the question on the next page of the PDF says, describe the relationship shown between the weight of the bat and the distance the ball travels. So when you're doing this, you want to give numbers. And you want to first explain what's happening on the x-axis. And as we go this way, the numbers on the x-axis are increasing, or the weight of the bat is increasing. So I'm going to start off with as, and that is not big enough for you guys to see, so I will change my font size. So as the weight of the bat increases, because again, we are going across the x-axis and it's going up by 0.5s. The distance the ball travels. Now we got to look at our graph. Well, if we take a look at our dots are going up. So in the beginning, at least. So as the weight of the bat, the distance, sorry, I forgot the ball travels increases. Now this is not perfect because we need to give some numbers. So as the weight of the bat increases from, we start at 0.5, there's no bat that can weigh 0. From 0.5, we got to find the number where it stops increasing to 2.5 pounds. The distance of that the ball travels increases from, and we got to look at our data. So it start at 0.5, at 1, I'm sorry, started at 1. See, when you're working on Kami, it's not as easy. So at 1, it was at 65 meters. And then it increased to, let's see, go back. And again, obviously, if we were doing this on paper, it would be easier, to 1.25 meters. Now, we're not done because that doesn't show the entire relationship on the graph. However, at a weight of 2.5, weight after 2.5 pounds, we will see that the distance that the ball travels starts to decrease. And you could put numbers here if you wanted to. There's probably typos in here because I'm the queen of typos. So as the weight of the bat increases from 1 to 2.5 pounds, the distance the ball travels increases from 6.5 meters to 125 meters. However, at a weight of 2.5 pounds, the distance the ball travels decreases. And you could put the numbers here if you wanted to. So it decreases from here, from 125 down to 72. You could put that there. I can't fit it. So I just picked this relationship. I actually don't know if this would be the relationship if we actually did this experiment. That's the data you could get. You could get other relationships. So we're going to discuss those relationships here, and we're going to draw little graphs. So one other possible relationship is as the weight of the bat increases, the distance the ball travels decreases. So our graph instead would start, if we were doing this, our graph would start here, and go down. I'm sorry, I'm wrong. We're going to redo this. I got to read it again. So as the weight of the bat increases, oh yeah, I'm right. The distance the ball decreases. So as the bats get heavier, your ball would go down. And that's assuming that that the ball is traveling a less distance at an equal rate, which we'll discuss at some point. So question 2. As the weight of the bat increases, the distance the ball travels increases. So again, we're going this way. Our weight of our bat is increasing. The distance the ball travels is increasing. So our line might look like this. All right, what are some other relationships? So as the weight of the bat increases, the distance the ball travels increases, but then starts to increase at a greater rate. So it's increasing slowly, but then at a certain point, it starts increasing. You'll see how the slope of our graph gets greater. And I don't know if we'd actually ever get that steep. That's almost exponential, but it starts going slower. I can probably redo that. So it doesn't look like it's like going to infinity. So here, and then it gets the slope of the graph gets greater. So like here, maybe it's going up by like 2s, and all of a sudden it starts increasing and going up by like greater numbers of 5 meters, then 10 meters, then 20 meters, then 40 meters. And that would be considered what we call exponential growth. But notice the difference. Here, it's going up by a constant amount. So the line is straight. Here, it starts off going up, the distance the ball travels is only going up by a little bit, but then it starts going up exponentially or faster. And then our last sort of relationship, and these are not the only 4, as the weight of the bat increases, the distance the ball travels increases, but at a certain weight of the bat, the distance stops increasing. So again, as the weight of the bat increases, so again, the line is going up, the distance the ball travels increases. So we're going up here, but then at a certain weight, the bat stops decreasing. So this is going to level off. And that should be straight. Don't ignore that little peak there. So again, these are various relationships that could be shown on graph. This is probably the most confusing one because as the weight of the bat increases, the distance the ball travels. So you have to start high and go down. But again, in your science classes, you guys will be practicing seeing these relationships between variables. So for this episode, you have to answer the quizzes. Our season finale will have you make a graph to practice that skill on your own. But thank you for watching the video, and have a good day.